In this video, we are going to extend the stable fluids algorithm in Julia to 3 dimensions, to then later on visualize it with Paraview to create these nice volume renderings. So let's get started. Hi and welcome to this new video. The extension to 3 dimensions is straightforward. It's something that you've probably read or heard a couple of times when it comes to scientific computing or simulations in general. But the question is, how straightforward is it? So let's try this out by using the stable fluids algorithm that we implemented in the previous video in the Julia programming language and extend it to 3 dimensions. So the original one was a 2-dimensional code and we will now work in 3-dimensional space. So in order to follow along with the video, I would recommend to watch the 2D version first and get familiar with it. You can find the source code file for both the 2D version and the 3D version we are going to write in the video on the GitHub repo of the channel. Going to 3 dimension does not change the equations much, so we still have our momentum equation as well as the incompressibility constraint, but now the u velocity here is a 3-dimensional vector as we are living in 3-dimensional space. We of course also have to adapt our mesh and our scenario. I now want to use a unit cube domain. Previously, we had a unit square domain with the extent 1 meter by 1 meter, and now we have a unit cube with 1 meter by 1 meter by 1 meter. And similar to the previous video, I want to use 2 force patches in opposite direction, which is creating those 2 streams of fluid that are colliding with each other, which we can then later on visualize in Paraview. The solution strategy will stay mostly the same. Of course, we have to adapt for the fact that we have an additional velocity component here, but I think we will see this along the way. So let's go down to the code and start with the actual transformation. In the last video, we used an approach to interactively visualize the vorticity or the curl of our vector field. This isn't as easy anymore in 3 dimensions, which is also the reason I want to use Paraview in the end. But for this, we need to be able to save out our velocity fields in order to load them into Paraview. So we can delete the plots import, and instead we will be using a package that is called WriteVTK. VTK is a common format to save the solution to scientific computing simulations, and this package simplifies this process. Then let's also adapt the constants here, because in the 2D case, we were using 250 points per axis. So we would then have 250 squared degrees of freedom. But now when we change to 3 dimensions, this would then be 250 cubed degrees of freedom. And this is actually almost reaching the limit on what you could actually do on your laptop here. Not to mention that it would be also extremely hard to visualize this in Paraview. So I want to reduce that to 40 per axis, which works fine on your machine. If you have a faster one, you can go higher. If you have a slower one, go lower. And then I also want to do 100 time step instead of 50. There is not much we have to change in the backtrace function, but we have to adapt the interpolation function to 3 dimensions by adding an interval in Z direction, as well as query points in Z direction. And then we also have to create our interpolator object with the interval in set that we handed over, and also evaluate the interpolator at the query points here. Then we can go to our main function and look at the mesh that we created. For this, we now also need an interval in set. So I will just copy this one down and use the set interval here. Then our coordinates array will no longer be a 2-dimensional array, aka a matrix, but it will rather be a 3-dimensional array, because each point in our 3-dimensional Cartesian mesh has a 3-dimensional coordinate. And this is rather straightforward. We just add another nested looping here by using the list comprehension, x for x in x interval, y in y interval, and z in z interval. And then I will just copy that down and adapt it for y, and lastly for the z. And then we can delete this line from the previous setup. A similar thing has to be done with the wave numbers. So here I will just add for k set in Wavenumbers 1D, and then just copy that down and call this Wavenumbers in y direction by using ky. And then lastly, we have Wavenumbers in z direction by using kset. And then accordingly, the norm is also built with all three components. So we also need the k set here for Wavenumbers. And then we also add this one in the nested looping. The decay does not change because it is just using this scalar Wavenumbers norm. And then this stability consideration where we remove 0 components in the Wavenumbers norm array will stay the same. Now we just have to also normalize our Wavenumbers in z direction. So we do normalized Wavenumbers in z equals the Wavenumbers in z divided by the Wavenumbers norm, or element-wise divided. Now there is probably the biggest change, since I want to adapt the scenario a bit. Here we were using 2 force patches by defining Gaussian blobs on our domain, but I think especially for the volume rendering later on, it is nicer if we have some sort of like a sharp discontinuity in the forces, and we can create that by using switch statements or by using if-else statements. So I will just copy that one out real quick such that we have it as reference. But what we want to do is use the if-else statement, which is basically like the numpy where operation in Python. And it takes a condition, and then based on the condition, it either returns an x or a y, depending whether it is true or false. And we want to use that in an batched operation or in a vectorized operation. So I will call it with a dot in the end. And then I want to have 2 force patches located in the domain. For this, I will say whether the x component of a coordinate of our mesh is greater than 0.2. And here I need to use the dot greater in order to have an element-wise operation. And the same for a dot and in order to get an AND operation. And say coordinates in x being smaller than 0.3. So I want the first force patch to be in the x interval from 0.2 to 0.3. Then let's also define the y interval, which shall be greater than 0.45 and smaller than, let me first get this one, and smaller than 0.52. And then we have the coordinates in z, which have to be greater than 0.45, and they shall also be smaller than 0.52. So we have it in the x-axis towards the beginning of the axis, and for the y we have it somehow centered and slightly above the middle line, if you could say so. And then we have to say when this condition is true, we want it to be 1, and if it is false, we want it to be 0. And this is our first force patch, and then we can create a second one, which will be similar. So I will just copy that for the start. And here we say that our x coordinate shall be greater than 0.7, but smaller than 0.8. So mirrored on this x-axis. And then the coordinates y shall be greater than 0.48 and smaller than 0.55. And so you see we have some sort of a small overlapping there. And I want a similar thing happening in that coordinate. So 0.48 and 0.55. And then we can delete these Gaussian blobs. And we are good with our new force definition that we can then use in the time loop. Okay, then let's go down and look at the pre-allocation of the arrays. So we now also need pre-allocation for the additional dimension. So let's do a backtraced coordinates in Z, which has the same shape as the coordinates in Z. The velocities in Z have the same shape as the coordinates in Z. And here you also see we are starting with an 0 initial condition, similar to the scenario in 2 dimensions. And then we have it in Z, a previous component. And we also have in the fast Fourier transformation or in the Fourier domain, we also have a Z component. And now before we enter the augmentation of the time loop, we need to create some sort of a container in order to store our trajectory or the evolution of these 3-dimensional velocity arrays over time to then later on write it out in the VTK routine, because I want to separate the computation from the write out. So for this, I will create an object that I will call velocity x trajectory, and this will be an empty list for the beginning, and the same for y as well as the z direction. And then we can start augmenting the time stepping. First, I want to change how the forcing is applied. I want it to be over a shorter period of time, so I will just increase the slope here. This is just that it looks a little nicer later on. And then we again have our application of the forces explicitly as mentioned in the stable fluids algorithm. Then we can use the backtrace function to also backtrace our coordinates in z using the coordinates in z and the velocity in z. And then for the interpolation of the positions, the interface has changed a bit because it now requires a z interval as well as the backtraced coordinates in z. And then the same here. So here we also need a z interval as well as the backtraced coordinates in z. And then I will just copy the interpolation once again in order to change it for the z velocity, because this one also has to be interpolated for our unconditionally stable backtracing on the streamline. So we do velocity z is given by interpolating velocity z previous at the backtraced coordinates given here. And then of course we also have to transform the z component into the Fourier domain. So this is also just another change. And then here we also need to apply the diffusive decay. And then we also have to account for it in the divergence. So I will just copy that down and say velocity z FFT element-wise multiplied with the normalized wave numbers in z direction. And then we also have to project it to get it back into incompressibility. So let's do the velocity z is pressure FFT element-wise multiplied with the normalized wave numbers in z direction. And then we also need to transform the z component back into spatial domain. So let's do that as well. And then we also have to advance the z components in time. Then down here we had our interactive visualization, but we can delete that because we do no longer want to do that in Julia, but later on in Paraview. And in order to do that, I want to save the arrays in our list that we can access them later on. So let me say save for visualization. And for this, we will use the push command to push into the velocity x trajectory, the velocity in x. And the same for the y direction, we push the velocities in y, and the same for the z direction, we push the velocities in z. And that's already the extension of our solver to 3 dimensions. So now it would already compute under the condition we haven't made any bugs in there, but we also want to write it out. And for this, we will use the WriteVTK package that we imported, and that works as following. For this, we will go back down behind our time loop, and then we use a function from this WriteVTK, which is called Paraview Collection, because we have a transient collection of VTK files. So you can think of a VTK file as one time snap of our velocity field. And since we have 100 time step, we have a transient collection of 100 VTK files. And we first give that one a name. I want to call that transient vector for the transient vector file. And then we use an Julia concept to say do PVD. So basically it is instantiating a new Paraview collection object and then calls it PVD such that we can then use it here in a local scope. And I would first insert the end here. And now we have to loop over our container to write out each of the VTK files individually. For this, I will add another progress bar and saying we are writing out to VTK. And then we do for iter in 1 to n time steps, similar to our main loop before. Let me insert the end first. And then we do VTK crit on the time step underscore $iter. So basically we create another file, which is a VTK file. And this one is supposed to have the name time step and then a variable depending on which time we are in, and it is based on a mesh or in a Cartesian grid on the x interval, the y interval, and the z interval. And then we do VTK, similar concept. We create a local scope here and then end in here. And then let's save out the vector file. So we do VTK at velocity is equal to an three-dimensional vector given by the velocity x trajectory, or maybe let me put that in a new line here, given by the velocity x trajectory accessed at the iteration, then the velocity y trajectory accessed at the iteration, and the velocity z trajectory accessed at the iteration. Then we have to compute the current time we are in, which is given as the iteration counter minus 1 times the time step length. So because this one goes from 1 to 100, and in the very first iteration we are at 0. So basically this is the time that we're currently in. And then we can access our PVD, our transient collection, and say PVD at time is VTK to associate the VTK file we wrote out in a separate file with our transient collection. And that should already be it. We can now open up a terminal again and then execute this file by saying Julia stable fluids FFT 3D.jl. Similar to other execution in Julia, we have the initial startup time with the compilation happening, but this time it will be way faster due to the fact that we're not using the plots package here. And we see now our computation has started. That's super fast. And then our writing out starts. And we can see it takes even longer than the computation itself. It's super interesting. And in the meantime, if you look at the file explorer, you see that Julia is creating these files in here. Basically, it's creating two kind of files. So first, the VTK file, so with an ending .vt1 for the time step 1, time step 2, time step 3, and so on and so forth. And then in the end, also this PVD for the transient collection. Then let's open Paraview to visualize our results. So first we will load in the collection by clicking on this folder button, and then we can navigate to the folder where the Julia code was located in, and then select the transient vector option here. So that will load it in. But then you see a new element in our pipeline browser on the left. We can click apply, and then we see our unit cube domain that we used for our scenario. But right now we don't see anything, and that is because we don't have anything displayed here. You can click on velocity by going to the top here and changing solid color to velocity. And then it also still does not show you anything because it's not doing the volume rendering yet. So we click on volume, and then you should be able to see that. You can use the mouse wheel to scroll in. First, I will change the background to black by going to the color palette here and then select black background. And what you see here now is the velocity magnitude. So we have a three-dimensional vector field for which we can select the x, y, and z component, or we can just use the magnitude, which is the norm of this vector. And here we see we have the two force blobs, which we created with our if-else statement. And you see that these are like rather discontinuous to the environment, so they appear as these boxes here. So if we then let the time run, they will collide with each other and create this beautiful flow pattern. So I will just click here, and then depending on your machine, this could either be fast or it takes some time. If it's super slow, then you might have to reduce the resolution in Julia. And you can use the mouse, click it and hover around in order to see what it does. Here on the right, I have the transfer function open. If that is not open for you, then you can go to the left and see in the properties panel that there is the coloring option, and here you can click edit, and we can use the transfer function to highlight certain parts in our volume rendering. So I will go back to the top and use this first frame button to return to the initial point in time. And then what I want to do is to cut off all the low velocity values to highlight better the values that are actually meaningful. So I will introduce another point here and bring it down, and you see the glow around these blobs has somewhat reduced. And if we let it collide again, it looks a little better, but we can even intensify that by moving it more to the right. But then you also see towards the end of the simulation, it is fading out. That is because there is diffusion in our simulation. So since we don't have any forcing towards the end anymore, since there was the decay or the prefactor in the forcing, all the kinetic energy will be diffused into heat in the long term. And I think it's quite beautiful to look at. We can even make it pop out more if we add a second one directly above here. Maybe not as far above like this, but then it looks like this. Feel free to play around with it. Probably you can spend hours with creating some super nice animations here. But the one that you saw in the intro was not the velocity magnitude, but the vorticity magnitude, which is the curl of our three-dimensional vector field. And we can compute that by clicking once on the transient vector. And then we go to filters, alphabetical, and then we have the filter called gradient of unstructured dataset. But we don't have an unstructured dataset, we have a structured dataset since we used a Cartesian grid, but it also works for that. And then probably it looks like this in the properties menu. If you click on the gear here, this will extend to the advanced properties, and then you can untick compute gradient because we're not interested in the gradient, but rather in the vorticity. And then we can hit apply, and then it has computed the vorticity for us. We can then select the vorticity here and change back to volume rendering. And here this is looking way more like what you've seen in the intro. So let's go back to the initial frame and let it run again. And to remind yourself, the vorticity, or more precisely the vorticity magnitude, is the strength of the curliness. So in other words, how swirly the fluid is at that point. And what you see towards the end, maybe it's even more clearer if we bring up it a little bit like that. You see that there are like these two rings, or maybe if we move it even more to here. Yes, I think that kind of shows it. There are these two somewhat rings of equal vorticity, and that's because we have fluid that is moving clockwise and counterclockwise in here due to the way that these two fluids interact with each other. And you can of course change the scenario, put the forces elsewhere, and see how that then looks in Paraview. But this is still not as it was in the intro, so we can also change the color map. So by looking at the heart icon here, so choose preset, and then we can select a linear color map. And in the intro, I think I used this one here. Maybe you don't have it installed, but you can also use the red one maybe. And then this, and then we can invert the color map in that, so that we have the darker colors towards the right for higher vorticity. And then starting back in the beginning, we can let these two collide. And that is basically what you've seen in the intro. So I hope you enjoyed that video and the extension to 3D. I must admit, this particular extension with the fast Fourier transformation is indeed rather straightforward, but a lot of the other simulation techniques that you have for fluids and also structural mechanics might not be as easily extendable to 3 dimensions as in that particular case. However, I think it's still interesting to see it for this simple scenario, and you can still make a lot of beautiful things here, and I would encourage you to play around. If you have a nice extension of the script, then feel free to open a pull request on GitHub to add it to the channel and make it available to a wider audience, which I think is extremely helpful for the community. As said again, you find the source code file on the GitHub repo for the 2D and the 3D case. If you enjoyed this video, then please leave a like and subscribe to the channel. There's a lot of similar content here on it. On the end card, you can click on similar videos and on a playlist, and I hope to see you in the next video.